Hello, my name is Erwin Ontiveros, and today we're going to explore metal quenching, a heat treatment process used to modify the mechanical properties of metals, particularly steels. Quenching may sound dramatic, and in many ways it is. It involves heating a metal to high temperature where its microstructure changes, and then you rapidly cool it to freeze in those changes. The underlying science relies on chemistry principles such as phase transitions, energy transfer, diffusion, and atomic structure. When we heat steel above its critical temperature, it transforms into a phase called austenite, which has a face-centered cubic crystal structure. This FCC arrangement has more interstitial space and can dissolve more carbon atoms than other phases of iron. Once the metal is fully austenized, we rapidly cool it, typically in water, oil, brine, or polymer solutions. This rapid cooling doesn't give the carbon atoms time to diffuse out of a solution. Instead, the trapped carbon forces the structure to transform into marstenite, a supersaturated body-centered tetragonal phase that is extremely hard but also quite brittle. This is a classic example of kinetic control versus thermodynamic control. Thermodynamically, steel wants to form equilibrium phases like ferrite and pearlite. But because quenching cools the material too quickly for diffusion to occur, the atoms cannot rearrange into stable structures. Instead, the system is kinetically trapped in marstenite, which forms almost instantly through a shear transformation rather than atomic diffusion. Different quenching media remove heat at different rates. Water and brine provide very rapid cooling, but also create a high risk of thermal shock and cracking. Oil cools more gently, reducing stress and making it popular for alloy steels. Air quenching is slower still and is used for air hardening steels that are engineered to transform even with mild cooling. This is similar to placing a hot glass dish in cold water. If the cooling is too fast, thermal stresses develop and cracking occurs. Real-world applications of quenching are everywhere. The hardness of a hammerhead, the edge retention of a kitchen knife, and the wear resistance of automotive gears all depend on controlled quenching. Even smartphone components rely on heat-treated alloys to survive mechanical stress. Another great example is drill bits and cutting tools, which must remain extremely hard so they can retain their shape, resist abrasion, and cut through other metals. Without proper quenching, these tools will dull almost immediately. However, quenching alone often produces metal that is too brittle for practical use, so we follow it with tempering, a process of reheating the quenched material to a lower temperature, typically between 150 degrees Celsius and 650 degrees Celsius. Depending on the desired properties, tempering allows some of the trapped carbon to redistribute or form fine carbides, relieving internal stress. This reduces brittleness while maintaining useful hardness. It's a perfect example of how controlled thermal energy can fine-tune material properties. In short, quenching demonstrates how atomic level structure determines macroscopic behavior, a key theme across chemistry, material science, and engineering. It highlights the intimate connections between temperature, microstructure, and the mechanical properties that make modern technology possible. And that is all. I chose to present about this since I'm majoring in metallurgical engineering, and this has been like the topic that really caught my eye and I really liked, is with metals and how the heat treatment makes them act differently. All right, thank you.